recall from last time. One. Yeah. F of X is odd. Then. Zero. Functions like this are things like y equals x, y equals x cubed, y equals sine x. And when they're odd, they look like this. So when you go from minus a to a, the total net area is zero. Cancel. Okay. And two, if f of x is even, then that is f of minus x, f of x. Then the function is something like this. Just kind of a mirror image about the y-axis. Then the integral from minus a to a, f of x dx. Well, you can just go from 0 to a and double. So these observations are useful sometimes. So for example, let's say so suppose I do something here where I want to integrate this. Well, this function in its totality is neither even nor odd, but its pieces are nice. This one right here is even. This one is even. And these last two are odd. So one thing that I could do is I can break this up this way. Actually, you know what I'm going to do? I'll break that. This problem you see are positive, but it doesn't affect the sign. Notice these are both odd, so these. So already my work. So this I will leave actually in this form. This one's even, so I'm going to use this little thread here. It's going to integrate from 0 to r and double it. I guess I'll go 6. 0 would have been affected again. Well, how about this piece right here? This is even, and I could have also done this trick here, but it's going to describe what this function looks like? Y equals the square root of R squared. Yeah, that's right. This is actually the upper half of the circle. Radius R. This area is 1/2 by R squared. So this piece is 1/2 pi R squared. And this piece is, well, what's your favorite antiderivative of 3x squared? What's the derivative of 3x squared? How about x cubed? There's another 2 here. And notice plugging in 0 for this is easy. So the answer to this I get a penalty. So that's how your life might be made a little bit easier by noticing even and odd symmetry. Now, of course, your garden variety function is neither even nor odd, so you can only take advantage of this. Don't just think that show up. But of course, every polynomial can be broken up into an even and odd piece. Okay. Any questions? Okay, here's another kind of application. So we're going to talk about the average value of a function. And from this, we get the mean value theorem. Okay. We've already had the mean value theorem as a derivatives. Now we're going to get one for integrals, which is actually related to the other. Okay, so let me ask you a question. So suppose that you made these 4 test scores. They're all weighted equally. What is your test average? So you made 100 on one exam, 90 and 80 and 70. What's your average? So good, good. That's a good. But how did you do that? That's actually a pretty smart way to do it. But that's because these scores were spaced out equally. In general, how what if it was like, 162, 43? So add all of them divided by 4, right? So and this is 85. So everybody's aware of that, right? I mean, the way you take an average, if you have n items of data, then you add all n items up and you divide by n. So if you've got 100 things, you want the average. You add all 100 things up and divide by 100. Everybody familiar with that? Now, let me ask you a question. So I'm watching the weather, and the weather dude says the high today was, say, 90 degrees, and the low was 60. Well, actually, let's say the low was 0. I'm pretend that happens. So the high is 90, the low is 0. So what do you suppose the average temperature of the day is? So 45, right? Add them up, divide by 2. Given the data I gave you, I can't expect you to make a more reasonable guess. But anybody criticize Just averaging these two for what the average temperature per day is. What's that? That's really, I mean, the day is 24 hours, right? You got some poor guy getting paid like, $5 an hour to go out and measure the temperature. He does this twice a day. One time he gets 0, one time he gets 90. Is this an accurate reflection of the day? Well, here's two things that could have happened during the day. Number one, it could have been 0. So here's 24 hours in the day. It could have been 0 all day until at 11:59 the sun exploded, and then at the very end you get to 90 because the sun is going right. Would it be fair to say that the average temperature on this day is 45 degrees? Probably not, because if you were out anytime during that day, except for that last minute, it's a 0, right? On the other hand, the opposite could have happened, right? It could have been a really hot day, and then pretty snowstorm, right? So if you were out for like 23 hours and 59 minutes, you think it's 90 degrees, and then at the last minute it drops. Here, I would say that if you want to cast a more accurate depiction of what the average temperature is, it's going to be closer to 0. It's going to be less than 45. Do I agree with that? On the other hand, here, I would say the average temperature is bigger. Right? Now, of course, another thing you could is could start at 0 and then uniformly increased in temperature until it got to 90 right at the end of the day. Would you say it's fair to say the average temperature here was 45? I would say so, right? Because you get this uniform, and I could have done it the other way, it might have decreased. Can anybody tell me what anybody give me the qualitative difference between these three? This is here, the average temperature, I think we all think should be less than 45. Here it should be greater. Here it should be equal. But we all kind of agreement on what it should be. What's the difference? Can somebody describe the difference in these three functions? We're talking about intervals here. See this box right here. The area under this box is 24 by 90, right? How much of this is occupied by the area under the black curve? Almost none. On the other hand, this box is also 24 by 90. How much of the area under the black curve of the box is occupied by the area under the black curve? Almost all of it. Everybody agree with that? This box is also 24 by 90. How much of the box's area that is occupied by what's in the black curve? Half of it. So the idea is get something like an average doing this, but do it for a function. Now, a function is continuous. It's sort of, as opposed to just taking measurements twice a day, taking measurements continuously in a sense. Here's the way that we can make our temperature reading. I've always thought this was kind of funny because I used to live in North Dakota, and you would get weird days like this. And if you just average it, it's not what they felt like. how could you get a better look at what the temperature is? Well, they don't want to take up time in the news, but he could sit here and say, well, we measured the temperature 25 times today, and here's a list of them. Right? Of course, everybody gets bored listening to that. But if you had that list of 25 points, and you average them, it's going to be probably more accurate than just taking 2 data points. Right? So what you can do is use more data points. So let's say that so let's just use this as kind of temperature. So you can think if you like, just to keep kind of a nice picture in your mind, you can think of this like, our average temperature. So here's my function here. It's 0 until the very end, 90 until the very end, uniformly going from 0 to 90. What can we do? Well, taking an interval from A to B, you might interpret this as your 24-hour day. And break this up into, so this is a practical problem. I am going to assume here, since we've sort of gotten beyond the theory and we're doing some applications, I'm going to assume that I break this up into equal times. Break this up into equal spaces. Maybe you break that up into 24 pieces because it's a day long, and you want your intern to go out and measure the temperature every hour. So this is X1 star, X2 star, XK star. So what you're going to do is you're going to send your intern out every hour, every minute. If you really want to use it, but I mean, you go out and take, 60 readings in an hour for 24 hours, right? I mean, that'd get a lot of data. And your intern's going to come back and say, well, here's the temperature the first time I measured it. Here's the temperature my second time I measured it. Here's the temperature the third time I measured it. Finally, here's the temperature the last time. Now, to get the average, what does your intern do? Adds up all those temperatures and divides by n, right? Now, what we were doing before was just taking 2 measurements. And I've always wondered about that on the weather. Like, how do they really know what's the high and the low? I mean, did they have somebody out there all the time? But well, now so what we're doing is we're taking all these values of function, a lot of them, and dividing by n. Now, the high and low is ostensibly with n equals 2, but you might send the intern out 4 times a day. You might send out every hour, so it's 24, I guess. I send out every minute, so now 1,440. You might send them out every millisecond, right? better start paying them. And this should be, would everybody agree as it gets larger and larger, this should be a better approximation of the average value, right? Because you're measuring more and more data on this. Now, I'm gonna make a little adjustment in here. Notice that, the delta X, the width of each of these intervals, they're all the same, right? Because I assume that I've broken up. What is the width of each interval for this particular situation? Okay, so what's the width of the entire interval? B minus A. Everybody agree with it? And we've broken it up into what, n pieces? So this should be right here. So let me massage this a little bit. And point out that 1 over n is equal to delta x over b minus a. That's just dividing both sides by b minus a, which I can do for the c bigger than that. So my average value of the function is f x star f x star over n. But that 1 over n is x star 1 over n is e minus a and delta x. So I'll replace my 1 over n here with delta x. So f average approximately 1 over b minus a times sum just writing this stuff right here, sigma notation. Now, if I make n bigger and bigger and bigger, this should be closer and closer to what the average value of the function should be. F average equals 1 over b minus a limit. Then goes to infinity. Of x star delta x. Now, here's your kind of first lesson. What I told you. This is a Riemann sum, isn't it? It's a sum of the form x, some values plugged into a function f times a little width. What does the limit of sums become? What's the limit of one of these sums, Riemann sum become? Right, when you take the limit of the sum like this, what does it always become? This is something that should be really integrated into the thing. A limit of a Riemann sum always. And the limits in this case, what interval are we on? This is the average value of the function. Let me kind of geometrically interpret this for you. At the end of the day, we kind of went through sort of the hardcore derivation. See why this makes sense. Just let me draw you a picture that illustrates. Suppose I have this function here. Now, for this particular function, I've drawn a positive, so I can really interpret this as an area. What does this function say? Well, I think of the function, see what the function is, it's determining the height. At any point, the function tells me what the height is, right? Let me read to you what this says. This says the average value is take my entire area, so the red area, and divide by b minus a. B minus a is that width. So you're taking the entire area under this curve, and you're dividing by the width. And what should you get? You should get a height. What this barfs out is this is the height of the rectangle that you would need to make it be the exact area. So I would say, would you say, let's see, if I average this value, this, it's about right in the middle. Do you think the average value would be higher or lower than this midpoint? I think it'd be a little bit higher. It's sort of clustered toward the top. If this were exactly flat or exactly straight like this, I would expect it to be midpoint. You've got more stuff at the top. I would expect whatever the midpoint is, this to be a little bit higher. So like maybe this is the average value. This is the height of the rectangle. So that this rectangle is exactly the same as the red area. What's the average value doing? So you take my area, divide by my width, and that gives you the height of the rectangle that you would need to have exactly the same area. And this is kind of, this more accurately captures, I think, what's going on. So for example, if you remember our example here, where it was really, really cold, right until the very end. The area under this curve is exceedingly small. And so what would the height of the rectangle be that has exactly that area? Well, yeah. In fact, that's probably even too big, I would say. Yeah, I almost definitely, I should take this down a notch. Probably it's gotten to the point where I can't even draw it, but it's probably something like that. The average value is a little bit above zero, but not much. Right? On the other hand, when it was hot most of the day, and then we had the big snowstorm, the area under this curve is humongous. If it hadn't slipped up a bit, it would have been almost this whole rectangle, but you've got this little sliver that's missing. So the average value should probably be just shy of 90. Or that's just perfect to recapture what we need. Everybody okay? So, for example, let's so sin x is something like this. Here pi. So part A, the average value is 1/pi. It's a length of the input. 0 pi sin x. 1/pi minus cosine x. 1/pi times. When I plug in pi minus cosine x, I get 1. And when I plug in 0 minus cosine x, I get minus 1. So I get notice that's a little bit more than I had. How about this? Notice this piece here, symmetric. One over power 2, now the interval's only power 2. That's the interval 0 power 2 of sin x. X is 2 over pi minus cosine x, evaluated by 0, so 2 over pi times, when I plug in power 2 minus cosine 0, I'm plugging 0, it's 1, plug 2. Notice that this is bigger than a half because this is sort of concentrated at the top. Questions? Um, find out value. Let me just, you know, really need to do this. I'll do it anyway. Let me kind of schedule this slide. X greater than or equal to 0 is equal to 2x. And if x is less than 0, this is minus 1 plus x. So it's a little flatter. It's okay. This function is a little bit different because it's defined two different ways. So we'll just follow our notes though. F average is 1 over b minus a, 10 over a b, f of x. Okay, so let me fill in some of this. What's a and b here? Good. So this is 1/8. So now the only missing piece of the puzzle is what's this? You can do this, by the way. You don't need really anything too fancy in calculus. You can do this just by computing areas, two lines. But I'm going to go through this. This is one of the cool things about intervals. This thing's piecewise continuous, so I can compute this fairly easily. Okay. So why did I break it up that way? Right? I mean, so I think you'd have to agree with me. The integral from -6 to 2 is the integral from -6 to 0, and then integrate from 0 to 2. Why did I choose 0? That's why. Why is this? Because that's the way the function is defined. Define one rule on one side of 0, another rule on the other side of 0. So I'm going to break it up that way to make my life easy. This is integral -6, 0. And when I'm on that side of 0, I need to be using this rule. Integral from 0 to 2. When I'm on the positive side of 0, I need to be using this rule. All right, let's troll this out. See, this first piece is going to be minus x plus 1/2 x squared. Evaluated minus 6 0. I love this kind of problem because you can always check. I've got the right answer. Derivative of this is minus 1 second. That's right. My favorite antiderivative of x squared, or is 2x is x squared. So let's see what shakes out this mess. When I plug in 0 here, I get 0. And when I plug in minus 6, I get 6 and a half of 36 is 20. So that's going to be 18.6. Plus, work this out here, this is going to be 4 minus 0. So what do I get? I get so I get 4 minus 24, negative 20. So this becomes negative 20 over. Okay. I'm going to give you all a theorem now. This one's kind of big. This is called the mean value theorem for chemicals. And like I said, this is intimately related with the mean value theorem. We did with derivatives here. Let's suppose that f is continuous on AB. Then there is a number C open interval with f of C equal 1 over b minus a. In other words, what this says, if the function is continuous, then there has to be a number between a and b, called c, where the value of function of c is exactly the value of the average value of the function. Let me kind of illustrate this. I'm going to illustrate this and then I'm going to actually prove this. Now, if you have so if you have a function that is continuous on the closed interval, what's one of the biggest things that we know? This is basically what it's like a derivatives. Any continuous function on the closed interval attains what? This is basically the whole reason why we did applied problems. If you have a continuous function on the closed interval, it attains its maximum. Looks like the minimum's right there. Right? And it looks like the maximum is at that right in. Notice that, you know, max. This is one of our, this is one of our inequalities about intervals. What this really says is the area under the black curve is bigger than the area that's topped by the red box, and it's smaller than the area that's topped by the blue top. So this bit right here, same total blue area. And by blue area, I mean all the way down to the bottom. This is one of the equalities we had back in the first definite interval. Basically, it says the area under the black curve is bigger than the red box, smaller than the blue box, right? This means that this leads to the common sense equation. Here's what this says. The average value of this function is less than its maximum and more than its minimum, right? Would everybody agree that the average value, the smallest it can be is the red value. The largest it can be is the blue value, and the average has to be somewhere in between. Do I agree with that? So it's got to be somewhere in between this y coordinate and this y coordinate. Maybe it's here. And because the function is continuous, there has to be a place where the value of the function is equal to. Now I'm going to make that very precise now. Average value has to hit the function. Okay, so let's do this more carefully here. Right. Let's let Apple. Now notice by the fundamental theorem of calculus, one f prime of x. What's the derivative of this equal to? Yeah, whatever. Here, that's. So, in particular, we observe that f of x is continuous on the interval from A to B. Those F is. And F of X is differentiable. The open interval, AB. And I know it's differentiable because it's derivative. There it is. That's that. So, by the mean value theorem, when we propose a derivative, there is a C in the open interval of AB with F prime of C equal to F of B minus F of A over B minus A. That was the statement of the mean value. And remember, all this says is there's some point between A and B where the slope of the tangent line of this function is equal to the slope of the secant line that connects the endpoints of the interval. Now, when we kind of deconstruct this, F of B is the interval from A to B of F of T to T. How did I get that? Just by plugging in B here. By the same token, what's F of A? What do I get when I put in A? Right, so that turns out to be what? That's right. You get the interval from A to A, which is 0. So F B minus F of A over B minus A is equal to F of B over B minus A, which is 1 over B minus A, interval from A to B of F of T to T, because that's what F of B is. And this is F prime C, which is little f of C. So F of C, 1 over B minus A, B. There should be 9. Okay. Any questions? Okay, so here's the question. Do you really need continuity there? Anybody thinking? So why help us try to draw a picture? You know, where let's say you can pick that out in one. Which have average on B not coincide. Average value is not coincide with the value of the function. I think how you might do that. Well, believe the mean value theorem, you have to make sense. Not. What about something like this? You're playing a right trade. Suppose I made value function this or half of it. And then this intuitive. Where do you think the average value is? I would think an average from these between. Is there any value of the function that's equal to the average value? No, because that line is not intersect like function anyway. Right? How did I cheat? By making it jump, right? So you do need continuity. Let me actually do the computation. Let's let f of x, let me mimic my picture. Let's say 1, if x from 0, 1, and 3, if so this would look very much like a function, right? Got that. That's 1. This is 1. Let's see how this works out. On the interval from 1 to 2, f average is equal to 1 over 2 minus 1 comes the interval from 1 to 2, but that's the x. Not 1 to 2, not that. That should be a 0. Because the interval is too long, and the interval is too long. So this is 1/2 interval from 0 to x dx. Now, just like I did before, I'm going to break this up sagaciously. Why did I choose to break it up that way? Because that's what the rules say, right? I've got one rule from 0 to 1, got a new rule from 1 to 2. So let's put my rules. This is 1/2 f of x. That's just 1. 1/2 f of x is now 3. So let's see. 1/2 x evaluated from 0 to 1 plus 3/2 x evaluated from 2. First bit gets me 1/2 minus 0. And the second bit gives me 3. I'm going to put into 3 minus 3. So that's going to be 3/2, 1/2, 4/2. Now, just because you're not continuous doesn't mean that you can't have value functions. Let me give you an example of that. What if I have a function like this? And somebody explain to me, but everybody agrees this function is not continuous. Somebody explain why average value, there must be some place where the average function is equal to the average value. Equal. Every y coordinate is counted for, right? Everybody agrees that this is the minimum value and that's the maximum value. Right? So the average value of the function is somewhere between here and here. And no matter where I draw that horizontal line, even if it's there, I'm going to hit some point on the function. Right? So the moral of the story is this. If the function's not continuous, you could have bad stuff happen where there's no value in the function that's equally average value. Just because it's broken doesn't mean it doesn't necessarily work. Okay. Any questions? You know where the 3 came from? Right, so the 3 is value function. The antiderivative of this is 3dx, or I'm sorry, 3x. 3x. That makes sense. Well, so the average value of this function, you can compare this the area under the curve divided by how long it's with it. That average value has to be a y coordinate that's at least that big and no bigger than that. So no matter what y coordinate you pick, if you draw a horizontal line, it hits the function. So there's some point on the function that is the average value, right? Up here, it's always hitting over here. And when it finally gets to this point, it hits this one, but not this one, because it's an open hole. And then it hits this part of the function like that. So no matter how you cut the pie, the average value is going to be some kind of function, even though it's not. Okay, other questions? I did want to say something about the well, this you all did pretty well on the quiz for the most part. Now, see, there's something you don't have. Next time you have some dialectics. All right, so let's see if we can kind of figure out how to do it. Well, it's, you all talked about this, it's important that you look at definition of absolute value of x. And this is kind of common sense, right? Okay, y'all, let me see how quick y'all, what's the absolute value of 7? What's the absolute value of -10? Wow, you all are fast. What do? You listen to what's coming out of my mouth, and then what do? If I say something positive, what do? You repeat me. If I say something that's negative, what do? Change it to positive. Right? So here's what you're doing. It says, hey, your ears say, Jim said something positive, so you left him alone. Jim said something negative, you made it positive. And how do you make something that's negative positive? By multiplying by -1. So that's what this says. We can now use this to get this is. It's interesting what this looks like, by the way, just for fun. This looks like x squared over here, and it looks like minus x squared over here. So basically what you did is you took the ordinary parabola, y squared, and you grabbed real hard on the upper hand and twisted it down. This is interesting because this is continuous at 0, and it's got a first derivative at 0, but it doesn't have a second derivative. 0, so this survives and follows. It's continuous at 0, got a first derivative at 0, the second derivative doesn't exist. Well, so let's get to the interval here. So if you want to do this, this is the integral from -3 to 0 plus the integral from 0 to 6. Now, why did I break it up this way? Because 0 is sort of the use point where I've got different rules. So let's see here. From -3 to 0, my rule looks like it's going to be minus x squared. Integral from the rule here is x squared. Like, okay, so far. This is my favorite antiderivative minus x squared is minus 1/3 x cubed. I evaluate that from -3 to 0. My other piece is we take 1/3 x cubed. Well, let's go through it. This is 0. When I plug in 0, I get 0 minus. When I plug in -3 here, I get -1 to the third power negative. So it's going to be positive 3/3 so it's 9. Negative cube is negative times another negative back to positive. 3/3 is 1/3. Okay, 9. This is going to be 216. 1/3 of that is 72 minus 0. So I get -9 plus 72 to 60. had one of the quiz problems. You had the velocity of some particle sine t, where t was in seconds. V of t was feet per second. What's the displacement particle on period of time? Well, the displacement is so if I start here, if the only information I've got is I start here and I end here. This is when time starts, and this is when time is up. But the only information I've got is I started here and I ended up here. My displacement is just measure the difference between these. That's exactly what it is. See where you started, see where you finished up. The difference in that is displacement. And this is the integral 0 to pi of v of t. So the fundamental theorem of calculus versus here. What's the antiderivative of velocity? Position, right? Position 2 pi minus position 0. That's exactly this integral. So working out this integral would mean no displacement. Favorite antiderivative of sine t is negative cosine. Good. When I plug in 2 pi here, I get -1. And when I plug in 0 here, I get -1. -1 plus 1 is 0. How about that? I started and finished at the same place. And this actually makes sense because this part is this will also be helpful part B, but here's why this kind of makes sense to me. If you look at sine t on the interval from 0 to pi, it looks like this. What this velocity is the velocity starts at 0, gets up to a maximum of 1, and back down to 0. So starts off, it's going really fast and slows down again. Now its velocity is negative. So he's going backwards, doing the same thing, right? So it kind of makes sense, doesn't it, that you would come back to where you start? Because here, you're doing some positive velocity, you're going slow, and then you pick up speed, and slow down. And then you do the same thing in reverse. So displacement of 0 makes sense. Now the question is what's the odometer going to say? Because really what happens is go fast and slow down, and go fast, slow down. So your odometer is not going to say 0, you went. How do we get distance traveled? Displacement, I just integrated the velocity. How about distance travel? Yeah, that's right. Your velocity's got a direction, positive, negative, right? The absolute value of that velocity is your speed. And that's what you got to do. You got to strip off the ability to tell what direction you're going. So distance travel should be the interval from 0 to 2 pi. Of the absolute value of sine t. This just measures the speed. And again, what are you doing? You're adding up speed. And this will give you, sort of, I think of an interval as a limit of sums, that's handy. You're adding up the little speeds and it gives you the velocity. Or not the velocity. This is traffic. This picture is also very useful for this, because if I want to integrate the absolute value of this, why did I split it up into these pieces? Why did I go from 0 to pi and then pi to 2 pi? Right, this is my breaking point right here. This is where I divided it up. Because from 0 to pi, sine t is positive. Right? So what's the absolute value of a positive number? You leave it alone. What about from pi to 2 pi? What can you say about the sine t? It's hanging below the axis. This is negative. And how do you take the absolute value of the negative? Change the sign. So this first antiderivative of sine is minus cosine. Evaluated from 0 plus cosine b is the antiderivative of negative sign is positive cosine. Now, basically, this should give me the distance traveled for the first bit of the trail, I. This should give me the distance traveled for the second. Both of these separate numbers should be positive. That's a big change. See what happens with this first one. When I plug in pi to cosine, I get -1, so I get negative 1, which is 1. And when I plug in 0 here, I get -1. That's going to be 1 minus 1 times 2. That's going to be positive. For the other one, I'm going to get 1, which is what cosine of 2 pi is, minus 1. So I get 2 plus 2 is 4. So the displacement of the object was 0. It ended up back where it started. But if you look at its odometer, it'll say, well, it traveled 4 feet. Come back to where it started. Okay. Any questions? Your all's quizzes have been proven, so that's a good thing. You feel like you all understand this all right? Okay, so we've got, I mean, we can start the quiz now, because I've covered everything that I need to cover before the test, and we'll get tonight. But I will give you the floor if anybody's got any questions. Well, just remember our review session tonight at, well, this afternoon at 5 o'clock. And if there are any questions, then I will let you guys start.